Okay, so welcome to the seminar Búsqueda de Nueva Física en Aceleradores y el Cosmos. I would like to introduce today's speaker. His name is Gabriel Marin. A little bit of his professional background. He's a master's student at the Universidad de Chile under the supervision of professors Gonzalo Palma and Francisco Rojas. Previously, he obtained his undergraduate degree at the same institution. His academic interests include scattering amplitude, celestial holography, and inflationary cosmology. So please go ahead, Gabriel.
Okay, thank you. So hi, everyone. Thank you for the opportunity to be presenting here. So today I'm going to tell you a story which is titled The Celestial Strings. So this was a work that we uploaded to the archive. You can check it out using this number that's in screen. And this was a work in collaboration with Lina Castiblanco. She's a postdoc at Newcastle University in the UK. Gaston Giribet, he's a professor at New York University in the US. And Francisco Rojas, he's one of my advisors. He's a professor at Adolfo Ibáñez University here in Chile. So, okay, all right. So here's the quick outline of my talk. So first, I'm gonna do a quick motivation about this work. So I'm going to introduce what's the celestial holography part. And I'm also going to introduce these celestial strings. Why do we care about strings? Then we're going to discuss about the celestial string setup in order to tackle some problems. So specifically, I'm going to discuss how to obtain some how to obtain and calculate celestial amplitudes, and as well string amplitudes. And finally, I'm going to discuss a specific topic that we computed in the paper, which is related to the field theory limit. All right. So as a start motivation, let me start by stating that quantum gravity is still one of the biggest puzzles in theoretical physics, where by just saying quantum gravity, I'm just referring to any theory that behaves like Einstein's general relativity at long distances. So now, in this topic, there has been significant progress in the topic of gravitational Borg theory in an anti-de Sitter spacetime, or just referred as ADS, which is a spacetime with negative cosmological constant, where one can make a holographic identification to a lower dimensional non-gravitational field theory, which is actually a conformal field theory, or just CFT for short, living on the boundary. So this concept is referred to as the ADS-CFT correspondence, and was first introduced by Juan Maldacena in the late 90s. So now we could then wonder, do we have anything similar in flat space? Do you have anything that we can call flat space holography? So in order to discuss this question, we first have to frame it into a physics perspective. So now, of course, in physics, we're quite interested in observables. So if we're going to study a quantum field theory living in the bulk, one of the stars observables to compute, at least theoretically, are scattering amplitude, which here I have represented by this double Penrose diagram. So now, if you're not quite familiar with Penrose diagram, let me quickly review it. So here's a Penrose diagram. Okay, so the blue lines corresponds to the world line of a massive particle, while the wavy red lines corresponds to the world line of a massless one. So now massive particles, they start and exit this diagram at these 2 points over here. So little I minus and little I plus, and they corresponds to past and future time like infinity. So in the case for a massless particle, they start and exit this diagram at these 2 lines over here, corresponding to big I minus and big I plus, corresponding to past and future null infinity, and we verbally refer to them as scri minus and scri plus. Okay, and we can also parameterize these 2 lines over here by these 2 parameters. So U and V corresponding to the retarded and advanced times. Okay, and you can then go on and study what's the structure of these null hyperspaces, and you're going to find out that it's composed by a real line times an S2, which is a sphere, which is the one that we refer to as the celestial sphere. Okay, and now let me just mention huge shout out to this point over here. So I0, which corresponds to spatial infinity. So this is a really cool point because you can find a really nice set of antipodal matching conditions happening to the Celsius sphere, which you can obtain by asking yourself, okay, what's the physics around this point? Okay, so now we can understand more or less what celestial holography actually means. So it refers to a duality between gravitational scattering in asymptotically flat spaces and a conformal field theory living on the celestial sphere. So more concretely, in other words, we say that a four-dimensional quantum gravity is equal to a two-dimensional celestial conformal field theory. So now we don't fully understand this dual description yet. We know it had some properties of conformal field theory. However, there are some certain subtleties that we have to take into consideration. I'm definitely going to mention this one in this talk. So yeah, this is why we don't fully write it to the CFT. We had this extra C before the CFT corresponding to the celestial behavior of this conformal field theory. Okay, so now let me answer to the natural question that could arise, and that's why do we actually believe in this duality? So in this presentation, I'm going to tell you, I'm going to discuss two hints. So now the first one comes from the study of symmetries. So you can see we have that the Lorentz group in d equals little d plus 2 dimensions acts on the sphere as the Euclidean conformal group in little d dimensions. So if you want to put some numbers, the Lorentz group in 4 dimensions acts on the sphere as the Euclidean group in 2 dimensions. Yeah, this is the first thing. Why do we think of a 2D CFT? So if you want to see it in a group theory point of view, we say that the proper orthogonal Lorentz group, so in 4 dimensions, so SO plus 1,3, which I have it described below, is actually isomorphic to SO2C quotientated by its center corresponding to Z2. So yeah, this is the first hint. There's a very nice matching of the symmetries. So now the second hint comes from the study of observables, so particularly the S matrix. So from a long time ago, we know that if we want to understand the asymptotic states of, for instance, massless particles, we can fully understand them by hitting some energies, so these omega I and some points on the sphere. So when we do that, we say that we're describing the S matrix in the energy momentum basis. So here's a picture of what's going on. So we have the initial data coming from Scry minus. We have the scattering process happening on the bulk, and we have some final data at Scry plus. All right. So now, if we want to understand what's going on the celestial sphere more effectively, instead of parameterizing it by some energies and positions on the sphere, we instead use some deltas and also some positions on the sphere. Well, this delta corresponds to the boost eigenstates on the sphere. When we do that, we say that we're working on the boost wave basis. So now you can go on and further show mathematically that this delta is actually the same as the conformal dimension of a 2D CFT. Okay. So now these two bases, they're not unrelated to each other. So you can actually go from one to another, and that's by performing this transform over here, which corresponds to the Mellin transform. So it's essentially an integration over all energies. So an integration from the omega from 0 to infinity and weighted by this delta. Okay. So yeah, in some sense, it's we're doing a similar task on what we do on standard QFT. So if you recall from your QFT courses, we start from position basis and then we go to the momentum basis by just performing a Fourier transform. So here we're doing something along the same principle. We're starting from the momentum basis and going to the boost wave basis of, or if you just want to call it the celestial basis, by performing this Mellin transform over here. Okay. So here's a little comparison of the two objects of interest in each basis. So of course, in the energy momentum basis, we're interested in computing standard amplitudes, which are given by the S matrix, as I have it over here. Now in this new basis, the boost wave basis, we're interested in computing celestial amplitudes, which are given by a correlation function of some operators that depend on the position of the sphere, and also these deltas. And we also have the information regarding if the initial if the particles are whether incoming or outgoing. So this is what these minus and pluses are telling us. And just to mention that these correlation functions, they have definite transformation properties on the global conformal group. So yeah, they transform very much accordingly to a 2D CFT. Okay, so now on the energy momentum basis, we know that we have manifest translation symmetry. And now in the social basis, instead, we have manifest Lorentz symmetry, which is equivalent, if you recall from the symmetry slide, is equivalent to the global conformal transformations on the sphere. Yeah, this is what's going on at the symmetry level. Okay. So also, I have to tell you a little caveat about these correlation functions, these social amplitudes, and that's while they behave quite nicely, there's also strange behaviors emerging from these correlation functions. And one of them is the appearance of some kinematic deltas coming from the energy momentum conservation delta from standard amplitudes, especially when computing lower point correlation functions. So lower point selection amplitude, for instance, 3 and 4 points. Yeah, there's this distribution behavior going on. So yeah, you could then wonder, okay, why is this a problem to start? So you can recall the 2D CFT knowledge and QFT knowledge. From a 2D CFT perspective, we know that, for instance, 3-point correlation functions, they're heavily constrained due to the conformal symmetry. In fact, they're constrained up to a constant. So yeah, there's no distributional behavior going on in that sector. So we're seeing it here. And also from the QFT point of view, we know a property called the operator product expansion, or just OP for short. So it essentially allows us to write down endpoint correlation function instead in terms of n-1.1s. So yeah, this distributional behavior is in some way, by using the OPE, gets propagated into higher point correlation functions. So yeah, if you want to strictly think that we're working on a 2D CFT, this could be a problem. However, we can use, for instance, leaf amplitudes to solve this problem. However, yeah, it could be also no problem at all. So this is still a discussing topic in the community. So yeah, if you strictly want to say that we're working with a 2D CFT, vanilla 2D CFT, yes, it is a problem. But yeah, just a small comment, a small caveat about these amplitudes over here. Okay, so now let me draw a really nice picture so we can have a better view on the topic. So for many years, we have been using this energy momentum variable, which here is represented by its energy, omega. And now I'm describing this new basis, this social basis. And I said how to go from one to another, and that's by performing this Melin transform over here. It's also still valid to study the conformal boundary by just using the position basis. That's always a choice that we can make. And of course, momentum and position basis are related by a Fourier transform. And also there's also a transformation from going to the position basis to the celestial one, and this was studied more recently. This is by doing this light rate transform, which is essentially an integration over this retarded time u weighted by some delta. Okay, so now there's a reason on why do we care about these three bases, and that's when studying low energy physics or just IR physics, in the case of gravity and gauge theories, seems to be quite convenient to use different corners of this triangle over here. So this is a concept referred to as the IR triangle. So for instance, we know that in the momentum basis, it's quite nice to study soft theorems where some amplitude factorizations are going on. In the position basis, it's quite nice to study the memory effect. I'm gonna give in just a second an example of this so it can be more clear. And on the top corner, so this new social basis, due to the manifest Lorentz symmetry, seems to be quite nice to study the asymptotic symmetry behavior of this theory. Okay, so here's the example in the case of gravity. So we have the leading gravity IR triangle. So on the bottom right corner, we have the gravitational memory effect, which was first studied by Sedlovich and Polnareff in the 70s. So it refers to a memory-like displacement of two detectors by the passing of a gravitational wave. So here I have a small animation on the topic. So you imagine that we have a circular detector with initial diameter d naught. So here's the gravitational wave passing through the detector. So it has an oscillatory behavior. And here's the final outcome of the detector. So if you compare these final diameter, you're going to see that it's different from the original one. Yeah, we say that in some sense, this detector remembers the gravitational wave. So yeah, this is the theoretical prediction. However, I know that there's some hope to measure it experimentally by using Project LISA, I think. There's hope to measure it in the future. Okay. So now on the bottom left corner, we have the subferrado theorem, which was first studied by Steven Weinberg in the 60s. So imagine that we have a scattering process with one external graviton attached to one of the external legs. So what the subferrado theorem is telling you is that if you take the energy of this external graviton to be soft, then you're going to see a really nice factorization going on, consisting on a universal factor times the original amplitude stripped from this soft graviton. So now this universal factor is very, very nice to study because, for instance, if you impose gauge symmetry, you're going to see some very nice physics. Particularly in this case, in the case of gravity, you're going to see the equivalence principle. Okay. And on the top corner, we have something referred to as the BMS symmetry. So in the 60s, Bundy, Vandenberg, Metzner, and Sachs, they tried to answer to the question of what is the asymptotic symmetry group of asymptotically flat spaces at null infinity. And they surprisingly found out that it was not Poincare, which was the naive expectations since they were working with asymptotically flat spaces. So instead, they find something that we now call the BMS group, which corresponds to Poincare by adding these translations. These symmetries over here, which are referred to as super translations, which are essentially translations that depend on the direction of null infinity. So here I have a picture so we can understand it. So in the case of the retarded time, this U, we say that it shifts independently at every angle on scribe. So yeah, this is just given by this function that's depending on Z and Z bar. So yeah, if it would be a ordinary translation, we would have a constant instead of a function. So yeah, this is why we have different arrows with different sizes on the picture. Okay, so yeah, this is the story for the leading IR triangle in the case of gravity. And of course, this story is not restricted only to gravity. We also have different versions of this triangle. So we have the gauge theory version. So we have a QED and Yang-Mills one. And more recently, we also know more the story on the subleading version of the IR gravity triangle. And of course, there's a proposal that it could be also valid to using different theories in physics. So for instance, we could have something as the cosmological IR triangle, for instance. And yeah, there are many more proposed and incomplete versions of this triangle over here. Okay. So now let me introduce the string part of the talk. So why do we care about string theory? So now let me start by stating that this is a fact. So the tree level for graviton amplitude in the celestial basis blows up in the UV. So now here I have to be a little careful because if you recall, the Bellin transform was integration over all energies. So from the IR all the way to the UV. So it doesn't make much sense saying UV in the celestial basis because we're mixing IR and UV. However, here I'm just making reference to what is the blowing part of the integral. And yeah, I'm just referring to the infinite part, so very high energies. Okay. However, at celestial string amplitudes, they are finite in the UV. And they're guaranteed to be finite by this exponential factor over here. So yeah, seems to be that if you want to have some intuition on what's going on the UV-like sector of the celestial CFT, seems to be that string amplitudes are a very nice playground to at least start playing. Okay. And well, a second motivation on string theory, which is now more related to the actual calculation that we did, is that there's this observation that if you start from string amplitudes, if you take the alpha prime going to zero limit, you recover field theory amplitude. So now this alpha prime is just a factor that's recurrently appearing on the string amplitude. So now, as a hand wavy argument to see that this is true, is to recall that this alpha prime is proportional to 1 over the tension of the string. So taking alpha prime going to 0 limit is essentially taking the tension of the string going to infinity, and thus having no string at all, but only point-like particles. So yeah, this is not that weird that we're recovering it in this case. So now, of course, this is just a hand-wavy argument. This more mathematical and vigorous way to see that this is actually true. So now this is in momentum space. And of course, as I just told you in a couple of slides ago, we can go from the momentum space to the celestial basis by just performing a Bellin transform. So we can individually translate each corner to the celestial sector, right? So now the question arises, is there any way that we can go from the celestial string amplitudes to the celestial field theory amplitudes? So yeah, this is the question that we want to answer. Of course, the naive expectation, right, is to ask ourselves, okay, can we just simply take the alpha prime going to 0 limit? However, we're going to see a couple of more slides in the future that, yeah, these limits does not work. Okay, so now the original work was done by Steve Erger and Taylor in 2018, where they computed the 4-point true-level amplitudes in the case of gluon and gravitons. And they found out that if you take the forward scattering, or just which is equivalent of saying the large R limit, where R is the conformal cross ratio, which is just a function of depending on the Z and Z bars. So yeah, if you take this limit, it provides you with the correct field theory prescription. Yeah, this is done at true level, and also there's this work of Tonei, Grivet, Gonzalez, Bohm, and Rojas, where they found that, well, they did the calculation at local level, and they found that if you take a correct modular space limit, you recover one Lobenian Mills amplitudes. However, now the full picture is not that clear. For instance, if you start adding some points, for instance, if you take 5 points, the number of the conformal ratios also increases. So these are, there are more than one. So yeah, it's not that clear which one you have to take to infinity. So yeah, it's the full picture is not that clear. And also there's the fact noted by these authors over here that you could take different limits for the R, for the large R. So instead of taking R going to infinity, you could also take R going to 0. And it also provides you with the correct field theory prescription. Yeah, the full picture is not that clear. So yeah, we want to analyze what's the case of the 5-point true level amplitudes in the case of gluons. What's the correct prescription? Okay, so in order to do that, here's just the most celestially picture that I could find in my phone. It was it's just a fresco from Galleria Borghese. So yeah, let's go and dig into the celestial string setup in order to make some calculations. Okay, so here's the setup. I've repeatedly said that you could take the Mellin transform from the momentum space to obtain something in the celestial basis. So here's the specifics. So if you start from a amplitude in momentum space, which is given by the right part over here, if you take a Mellin transform for each external energy, you obtain the celestial amplitude. So now, since we're dealing with massless particles, we could also take this null vector parameterization that I have on display. So it's we're essentially parameterizing the four momenta in terms of some energies, so this omega, and these two complex variables, z and z bar, representing points on the sphere, which are just done by performing a stereographic projection of the sphere into a complex variable. So yeah, we just perform that. And we also have this data, which is just telling you the information whether the particle was incoming or outgoing. Okay, so we now have to obtain celestial amplitudes. Okay, perfect. We now have to deal with the how to compute string amplitudes, right? So now, okay, so we need to compute these amplitudes that I have over here. So this is 4-point true level string amplitude in the case of operator strings. So now this is quite different as one sees in the typical QFT courses. So in QFT, we see it's just compute like the S channel for 4-point amplitude, right? Which is described as point-like particles. So the difference is that here we have surfaces. So we have a 2-dimensional worldsheet. So we need to compute this in some way. And so now the problem is that we don't know how to compute this as I just showing you. So now we can also do some tricks. So we can rely on symmetries in order to obtain simpler and calculable expressions. So particularly, we can use conformal symmetry to map the left-hand side, which, as I told you, corresponds to a 4-point true-level string amplitude. So here is labeled by 4 choice of momenta. So P1, P2, P3, and P4. We can map that into a sphere with 4 insertion points. So just B1, B2, B3, and B4. And yeah, we can do that so that this sphere actually presents the same topology as the original amplitude. So now, fortunately, we do know how to compute the right-hand side. So now let me quickly shift our attention to understand how do we do that. Okay, so as I said before, this is the sphere with 4 insertion points. We can parameterize these insertion points by some angle, or we could just say it's just a parameter and we call it x. So we have x1, x2, x3, and x4. And of course, naturally, since we're dealing with a quantum theory, these parameters, we have to account for every single possible insertion, right? So visually, this means that these parameters can be moving around on the sphere. So yeah, essentially, the amplitude will be proportional to 4 integrals, right? So this is accounted to every single possible insertion. Okay, so this is quite complicated to do as it is, because just 4 integrals is not that nice to always compute 4 integrals, especially for a 4-point amplitude. So now, again, we can resort into symmetries to obtain simpler expressions. So in this case, we have the SL2R symmetry. So this symmetry allows us to fix 3 of the 4 insertion points. So we can fix V2, V3, and V4. So yeah, in other words, the only parameter that is free to be moving around the sphere is just the V1. So this translates to the level of the computation that we now only need to compute just 1 interval. Okay, so this is the story, of course, for 4-point amplitude. Now, in the case of 5 points, which is the one that we're interested, it's quite similar. So instead of having 4 insertion points, we now have 5. So this is the adding B5. So naturally, at the level of amplitude, we will need to compute another integral. So yeah, just 5 integrals. However, we can again resort into SL2R symmetry to reduce it to fix 3 of the 4 insertion points. So essentially, we now only need to compute 2 integrals of some weird function. So yeah, that's just the string calculation just at the surface level. Yeah, it's just 2 integral with some weird and complicated function that we're going to see later on. Okay, so moving on into the specifics, we know that the true level maximum helicity violating amplitude for the n equals 4 and 5 gluons in the type 1 superstring is known to follow this factorization over here that I have on display, which consists of a multiplication between the Yang-Mills true level amplitude times a string factor. So now this string factor over here, the f sub I3, is the one that's going to be carrying around all the integrals that I was just saying you before. Okay, so this factorization is known to hold for n equals 4 and 5. I think there are some generalizations to general n. However, I know that for a fact that sometimes it's very difficult to put the string factor into an integral form. But yeah, there are certain generalizations. Okay, and also these Yang-Mills amplitudes over here is just given by the Part-Taylor formula, which I here have on display for the endpoint case, which is written in the spin helicity variables corresponding to these numbered triangular brackets. Okay, and we also make this choice over here. So this Sij corresponds to some invariance, which if we use the null vector parameterization that I showed you before, we can put in this very nice, simple, and compact way. Okay. So moving to this more specific. So here's the string factor with the small redefinition for this Si. So here we have a neighboring-like definition. So okay, here's the full expression. And I know it's quite cumbersome to see, especially at first glance. However, let me say a few remarks of this expression over here. So, for instance, we can immediately see that we have a double integral to compute, so an integral over x and an integral over y. So this is the remaining integrals that are still present after doing this SN2R fixing that I was telling you a couple of slides ago. And we also see that the alpha prime parameter is putting this, it's on every single exponent, right? So it's not on the dependence of alpha prime is not that trivial. And we also have a factor overall of alpha prime square that is, for instance, on the V5. So yeah, it's quite non-trivial to see, but at first glance. Okay, so essentially we know how to write the 5-gluon string amplitude in the momentum space. So we can go to the celestial basis by just performing this Mellin transform, right? So this is what we did next. So we obtained this expression, which again is quite cumbersome to see. However, it's a little bit less than the other one. However, again, I can tell you about some nice features. So the story one is that now this alpha prime dependence is now fully factorized out of the integral and put in a very nice and simple way, and it's very trivial. So we just have alpha prime to the beta, where beta is related to this delta. So yeah, we can immediately see that the alpha prime against zero limit it's not gonna go into a very nice direction because we just obtain a flat zero. So yeah, this is not the correct limit to consider. And well, so going on back to the expression, we have some gamma function. We also have some conformal ratios over here, and some zi and zij bar dependence on the first line. And on the second line, we see that we have some f's, we have some c's, and these are your functions of the zij and zij bar. And this a over here, which is to the b minus 2 power, is just a function of zij, zij bar, and a complicated logarithmic combination of x and y's. So yeah, okay, we essentially have a factor and a double integral of the weird function. Okay, so we have the celestial string amplitude. So now let's move on into the exploration to find, if any, its field theory limit. So here I have on display some suitable candidates to further consider. First, we have the hard scattering limit. That's the one that we can use. We have the Collier limits, soft limits, forward scattering limit, radial limits. So we picked this last one, the radial limit. They have a whole story with string amplitudes that I'm not going to go into detail. So now, in general, when considering higher point amplitudes, these radial limits, they roughly branch out into two categories. So you can consider single and multi-radial limit. So the first one just roughly corresponds to taking one of the internal energies to be the dominant over the scattering process, while the last one, the multi-radial limit, you allow more than one of the internal energies. It is just roughly. So we picked the first one, which, spoiler, provides us with the correct field theory prescription. So yeah, here's the single radial limit 101 basics. So if you recall, we had this definition for these Mendelssohn invariants SI. So I ranges from 1 to 5. So we need this P6 redefinition. So in order to the formula to make sense. So yeah, we have 5 selections of this S. Okay, and it's also convenient to define this new momentum invariant, which is called kappa. So it's defined in terms of S2, S3, and S5 in this following form. So we know we can take S1, S2, S3, S4, and kappa to be the 5 independent momentum variables. So now, as a quick note on the topic, if you have an endpoint scattering process, the number of independent momentum variables is this number over here, as I have, is 3n minus 10. So if in our case, n equals to 5, so 3 times 5 is 15, minus 10 is just 5. So yeah, from the 6 selection that I have over here on the top, we just have to pick 5 to be the independent ones. So yeah, this selection that I have on display is a valid choice. Of course, there are many more. So now the single radial limit statement is the following. So we take S2 going to infinity, and we hold S1, S3, S4, and kappa fixed. So if you see from the definition of kappa. If we take S2 going to infinity, we also have to take S5 also going to infinity, so in order to kappa to be fixed. However, there's no problem at all to doing that because S5 is no longer one of the independent momentum variables, so we're good. Okay. So this limit that I have over here, this definition is quite nice to study in the momentum basis. However, when going to the social basis, it's not that friendly. So with a little bit of a thought process, we can translate the single radial limit statement into this following set of kinematic collinear limits. So it's just a limit on the ZAJ bars. So we take Z12 going to 0, Z34, and Z245. And implicitly, we're also taking the same limits for the ZAJ bars. And when taking this limit over here on the celestial string amplitude, we find that the leading order term is the expression that I have here on the bottom, which is exactly what you would have obtained if you start from a 5-point gluon amplitude from Young-Mills. So yeah, we say that this limit over here is providing us with the correct field theory prescription. However, we found something interesting, and that's if you just take the first limit, we also recover the same expression. So yeah, at the end of the day, we say that the field theory prescription is just provided by a single set of kinematic collinear limit. Okay, so now here's the, as I like to say, the collinear table. So on the left-hand side, we have the collinear limits, and on the right-hand side, we have the general form of the x and y dependent integrand. So if you recall, when we had the celestial string amplitude, we had some constants and some z bars, and we had a double integral on x and y. So this is the integrand of that double integral when applying this collinear limit. So yeah, we just analyzed the first line. However, it could be interesting to study the hierarchical behavior of these multiple limits that we can take. For instance, by taking a different one and performing a suitable change of variables, we could obtain and recover the 4-point celestial string amplitude. That's something that we could do, for instance, in the future. Okay, so now to conclude, let me say just a few words. So we successfully studied the field theory limit, right, of the celestial amplitudes in the case of 5 points, where we found that a set of kinematic collinear limit inspired by the single radial limit was the correct prescription, as I have it on display over here. So now we also saw that this is not the most general one to take. So the most general was taking just this single configuration over here. So just C12 going to 0. However, now the question remaining is there any generalization of this result? So yeah, the answer is not that clear because of the increase in difficulty when you go, for instance, for 6 points. Yeah, the story is quite different and quite complicated. So yeah, however, I do think that the limit should still remain on the kinematic sector. That's for sure. And also, I didn't have time to discuss this in the talk today, but these two are the topics that we also computed in the paper. So we also computed the conformance of theorem in the case of fat gluons, in the case of type 1 superstring theory, where we saw that the field theory also arises from the low energy of strings. So this is a result that it's known in momentum space. So we also confirmed that it is also valid in the celestial basis, which is not that trivial to say. So yeah, basically it's just a statement regarding a 5-point amplitude on the left and a 4.1 on the right. This is one topic, and we also discussed in the case of gravity the map that this is sort of mapping between this puncture string worsted CFT and the celestial CFT. So concretely, we did it in the high energy limit, so hard scattering. So we essentially started from this expression over here, corresponding to the scattering of n gravitons. We computed and did an integral approximation, and we found that the saddle point equations are given by the scattering equations that I have over here, which are a key formulation in the Cachasso-Hien-Yang, or just CHY, formulation of scattering amplitudes for massless particles. and they naturally appear at low energy, the low energy limit. So it's quite nice that we're seeing a relationship between high energy and low energy. So yeah, now the punchline is that a single configuration of n momenta of closed strings gets mapped into n minus 3 factorial possible variates operator configurations. So yeah, this is the end of my talk. So thank you very much for your attention, and I'm happy to take any questions if you have them.
Well, thank you, Gabriel, for your interesting talk. So let's move on for questions. Does anybody have a question? Please go ahead.
Hello.
Hello.
We can hear you. Go ahead.
Okay, thank you. So it was not very clear to me, and I like if you can explain that again. The triangle, like what exactly does it represent? Is it just a change of basis, or yeah, I'm not getting it very well. Please.
So these triangle or
Yes,
this one in
yes,
the case of
that,
variable.
yeah.
Okay, this one.
Yeah.
Yeah, just a triangle representing on what are the three options that you could three basis options that you can use to understand the conformal boundary of non-infinity. Yeah. It's exactly that. Yeah.
Okay,
So
but omega and u are the momentum basis and the position basis. Is that what I? Yes.
Yes. So, sorry. The omega is the corresponds to the momentum basis. The u the position basis. So this u is if you recall the here you have it, the Penrose diagram explanation. This u is this variable to describe the non-infinity. So describe plus. So it's just the choice that I choose to put it here, and this delta corresponds to this variable that we use in the celestial basis. So yeah, omega represents the momentum space, u position basis, and delta celestial basis. So yeah, it's a relationship between these three. Yep.
Okay, got it. And another question: why the name celestial?
Why the name celestial?
Yes.
I think it's that's a really that's a good question. So I think it has some inspiration from the celestial sphere from astronomy. So I think I'm never an expert on astronomy, so take it as a thought. So
that's fine.
So in the case of astronomy, the celestial sphere corresponds to just all the light that we receive from the Earth. So if you just look at the sky, we're just every single point that you see. So the stars correspond to they're living on the celestial sphere. I think it's just the term they use in astronomy.
Okay, thank you.
Thank you for the question.
Anybody else?
What is the relation between Feynman and Penrose diagrams? The relation between both diagrams. Can you explain in more detail the relation between Feynman and Penrose diagrams, please?
The relationship by Feynman and Penrose diagrams. Okay, so Penrose diagrams we typically use to describe what's going on the geometry of the space that you're working with, and and Feynman diagrams are just diagrammatic representation of a scattering process. So you could say in this example over here, in the case of flat space, the Feynman diagrammatics are happening on the bulk. So I think I have it over here. So the Feynman diagrams are happening here. So the interaction are occurring on the bulk, and just the final outcomes. So the particles that we can actually measure, they are located on these lines over here, which we're in the case of massless particles, they just correspond to these square minus and square plus. And in the case of massive ones, we're measuring them on these 2 points over here. So the past and future time like infinity. Hope that that's clear.
Okay, thank you.
Yeah, I can say it's just like a closing word of that question. So yeah, Pareto diagram, just to understand what's the geometry of the space. And yeah, Fermat diagram is more a quantum statement of a quantum version of to do calculations more effectively.
Okay, Jonathan, please go ahead.
Hello, can you hear me?
Hello.
Yeah,
yeah, I can.
Hey,
Hi,
thank you, Gabriel, for accept the invitation and very nice talk. And could you explain more what is the concept of bulk, or it is not clear for me?
So okay. So first, let me thank you for the invitation. And okay, so now the concept of bulk, when we say that, so in the case of this, let me see a good picture. So here in the Pareto diagram, when we say bulk, we just referring to anything happening outside of these lines over here. So nothing going on the boundary side. So yeah, what's going on the all these region over here. Yeah, this is the bulk, and the boundary we're just referring to these lines. So square minus, square plus, I minus, and I plus, and I zero, of course. Yeah, and the bulk, it's just everything going on inside that we don't know how to deal with, because we don't know how to do compute the exact scattering. We don't know how to deal with these interacting Hamiltonian, right? That's just a problem from quantum mechanics. It would be cool that we know how to do that. However, it's just the world that we live in. So, yeah.
Okay. And celestial amplitudes are related just to conformal field theories, or could be related to other theories?
Yeah, that's a very nice question. So we say that they're similar to a 2D CFT because they transform like a 2D CFT. So it has these very nice transformations. However, it has some differences. So the one that I was saying, so these Dirac deltas present on the social amplitudes. So we can see it, for instance, here. Let me search for it. Over here, for instance, we see that this social amplitude, it has a delta function at the end. So yeah, it's if you close your eyes and forget about this delta, this looks very much as a 2D CFT. So that's why we say so. However, yeah, it has some problematics that we have to deal with them if you want to work with a 2D vanilla CFT. However, if you say, okay, we're just seeing a different theory over here, it's not a problem at all. So yeah, these celestial amplitudes, they're quite related to the CFT, but not quite. So that's why we add this extra C at the beginning. So CCFT.
Yeah. Okay. These amplitudes are only for 3 level, or it is inclusive fine to at loop level?
No. Yeah. I know that there are some studies of what's going on at the loop level. Yeah, for instance, these authors over here, they computed what's going on the here. What's going on the loop level at just one loop. However, I would say that it's not that very explored what's going on the celestial loop level. Yeah, I know that this is just recent line of research. So people are trying to deal with the more basic and easy stuff first. So just true level before moving on to what's going on in loops.
Yeah. Okay, I see.
Thank you for the question.
Yeah. Thank you.
Thanks.
More questions, guys. Jorge, go ahead, please.
Yes, it's in the chat.
Oh, it's in the chat. I don't know how to pull the chat here.
Sorry, it's because I'm in a library.
Sorry, what?
I'm going to ask it here.
Okay. Okay, perfect.
Okay. Firstly, what an amazing talk. It's a very
Thank you.
good talk. Secondly, I'm new to scattering amplitudes, and my question is about the why you can use the Parquet-Taylor formula. I have seen that you can use the Parquet-Taylor formula in QCD, for example, like when you compute gluon amplitude. Why you can use it here is because you have massless particles, or is because well, gravitinos, I don't know if they are gravitinos, are very similar to gluon.
Okay. Yeah. Yeah, that's a tough question to answer, especially me, because I'm not a huge inserted on the string theory world. So yeah, this is just a result from, so this factorization over here is just a result from the early 2000s. Yeah, it was obtained by Steenbergen and Taylor, also the same Steenbergen and the same Taylor. So yeah, so this factorization is known to happen in the case of open strings. So they're representing gluons. So yeah, it's really nice that you can do this separation, because you're like, okay, saying the gluon part is represented by this term over here, and the string part by these, we call it the string factor. So now it's really nice that you can recover the gluon term by just the field theory amplitude. So you can recall that you can use the Park-Taylor formula in order to compute the n-point gluon scattering amplitude. So yeah, this is a very nice separation that's going on. So now the specifics on why do we have this separation, these factorizations? I don't think I can answer that because I'm not a huge expert on these calculation of string theory. So this is just a result that we used. So yeah, but yeah, of course, we in this case, since so I can here move to the slide of over here. So yeah, since we're dealing with particles that are starting and ending on scribe plus, and see if you can recall here, only massless particles start and end at these lines over here. We have to be working with massless particles. So in the case of gauge theories, you have two choices. You can either use photons, or you can use gluons, or you can study gravitons in the case of gravity. We wanted to just study the gluon scale. So yeah, I know that I haven't answered directly your question, but yeah, I don't think I can say answer to the specifics on why these factorization actually goes up.
Thank you so much. Again,
Thanks.
that was a very amazing talk.
Thank you very much. It was a pleasure to hear you. Long time no see.
Yes.
So we have time for another more question. So if there's no more, thank you again, Gabriel. It was a really very interesting talk. So we hope to see you again in another seminar. You are very welcome.
Okay, yeah. Thank you very much for the invitation. And hopefully I can go sometime in the future in person. So yeah, thank you very much.
Thank you.
Okay, thank you,
let's
Gabriel.
finish. Let's
Bye-bye.
finish the talk for today. Bye.
Bye. Bye.
Bye.